Okay, we have a nice long answer problem here on some ionic solids, lattice energy, things like that. So a student investigates the enthalpy of solution for two alkali metal halides, lithium chloride and sodium chloride. So enthalpy of solution, we're talking about the energy associated with the dissolution of the solid. You put it in the water and it's going to dissolve and dissociate, and there's an energy exchange there. So we're studying that. In addition to the salts, the student has access to a calorimeter, a balance with a precise balance, and a thermometer. So we've got some stuff to work with here. So to measure delta H solution for LiCl, the student adds 100 grams of water initially at 15 degrees Celsius to a calorimeter and adds 10 grams of lithium chloride solid, stirring to dissolve. After the lithium chloride dissolves completely, the maximum temperature reached by the solution is 35.6 Celsius. So what we're doing is we've got some water and we've got some lithium chloride. As it is dissolving and dissociating, it's heating up the water, right? We're going from 15 to 35.6. And we're going to use that temperature change. This is calorimetry, right? We're going to use that temperature change to figure out delta H solution for LiCl. So calculate the magnitude of the heat absorbed by the solution during the dissolution process, assuming that the specific heat capacity is this figure. So how are we going to do this? Well, we know, first of all, that Q equals mc delta T. Heat exchanged is mass times specific heat times change in temperature. So let's go ahead and plug those in right here. So for mass, we have 100 grams of water and 10 grams of lithium chloride. So we need to be using the mass of the solution, so we have to add those together. We have 110 grams of solution total, right? Now, they're giving us the specific heat, right? Where did they put it? Yeah, right here. 4.18 joules per gram degree Celsius. And then we're going to plug in the temperature difference. Remember, it's always T final minus T initial. So 35.6 minus 15 degrees C. So we're going to plug all that in. If you're doing this on your calculator, probably the best thing to do would be to get this first and then multiply by the other two, right? We want to get that difference so we have one figure right in there multiplied by the other two. And we're going to get 9.47, 9,470 joules or 9.47 kilojoules. Okay, so that is the heat absorbed by the solution. So the solid, lithium chloride solid, is releasing heat during dissolution, and that is being absorbed. By the solution, which causes the water to heat up, and that's what we measured in order to be able to do this. So, determine the value of delta H solution for LiCl. So this may seem a little confusing, but it's not too hard, right? We have a heat exchange for a certain mass of lithium chloride. We just need that per mole instead of that. So let's figure out how many moles we had, and then we'll get kilojoules per mole. So if we had 10 grams of LiCl, that's we use the periodic table. We know that the molar mass is 42.39 grams per mole. So moles on top, grams on the bottom, so that grams cancel. And that is 0.236 moles, right? So this is the heat that was absorbed by the solution when this many moles of lithium chloride dissolved. So now what we need to do is we need to do two things. We need kilojoules per mole, so we just put kilojoules over moles. But we also have to understand that this is asking for delta H of solution. Part 1 said the magnitude of the heat absorbed by the solution. But heat absorbed by the solution is heat released by the solid. So if we're getting delta H for LiCl, this is specific to this substance. We do need to flip the sign. This is going to be negative 9.47 kilojoules over 0.236 moles, and that is going to give us negative 40.1 kilojoules per mole. So, so obviously the arithmetic is pretty straightforward. We're getting moles, and then we're just doing kilojoules per mole over moles to get kilojoules per mole. The sign thing, though, we just have to be a little careful. You would get half a point off if you didn't get that negative sign in there. But maybe if we had forgotten to do that, we would just get the 40.1. But then remember, the delta H has to be negative because the dissolution is releasing heat, right? And that's what's heating up the solution. So maybe we would do the arithmetic and go, oh wait, I think I have to make this negative because this is releasing heat. The dissolution is releasing heat, so it must be exothermic. So anyway, that's that. Now, to explain why delta H for NaCl is different than that for LiCl, the student investigates factors that affect delta H solution and finds that ionic radius and lattice enthalpy, which can be defined as the delta H associated with the separation of a solid crystal into gaseous ions, contribute to the process. The student consults references and collects the data, this data here. So we're talking about lattice enthalpy and ionic radius. So when you have ions in a lattice, there's some amount of energy that is associated with pulling them apart, which into what would be the gaseous state. So we're talking about the interactions in the solid. How much energy would it take to pull all of them apart to where they're not interacting? And obviously ionic radius has something to do with that. Sodium plus is bigger than lithium plus. And then we also need to talk about solvation. How much energy is released when those gaseous ions get into water and get to make all of the favorable electrostatic interactions. So knowing that sodium plus is bigger than lithium plus, we want to write the complete electron configuration for the sodium plus ion in the ground state. So now we're kind of bringing in some other concepts. So if we look at the periodic table, we would know that sodium is 1s2, 2s2, 2p6, 3s1, right? So that's the ground state. That's the ground state for neutral sodium. And so sodium plus is going to lose one electron, so it's going to lose this 3s electron. So the sodium plus is 1s2, 2s2, 2p6. This is essentially neon electron configuration, which is why it's so easy for sodium to lose an electron, so it can attain the noble gas electron configuration. Now, using principles of atomic structure, explain why the sodium plus ion is larger than the lithium plus ion. So this is very straightforward. It's not really asking anything more than just asking you to go, okay, lithium plus just has that one shell, right? Lithium is 1s2, 2s1, right? Normal, right? Lithium is 1s2, 2s1. So if we lose that, if we get Li plus, we lose that outermost electron. Li plus is just 1s2. Right, 1s2, it has helium electron configuration. So lithium plus just has that one shell with the two electrons. But sodium, right, we just said, is going to be 1s2 and then 2s2, 2p6. 2, 3, 4, 5, 6, 7, 8. Sodium has 2 electrons in n equals 1 and 8 electrons in n equals 2. So n equals 1, n equals 2. The outermost shell is n equals 1. It's only got one shell. And the outermost shell is n equals 2 for sodium. It's got 2 shells. So we're just talking about shells, right? N equals 2 versus n equals 1. Right? Another shell, we need more electrons. It's got to get bigger. Every shell is further away from the nucleus. N equals 2, 3, 4, 5, 6. Every time you add a shell or you increase the principal quantum number by 1, you're making the atom bigger. So that's why atoms get bigger as we go down the periodic table. So sodium is right below lithium. It's got to be bigger. Now, which salt, lithium chloride or sodium chloride, has a greater lattice enthalpy? So when here we're talking about Coulomb's law. So when we're talking about lattice enthalpy, there are two factors. You have a cation and an anion, so you have some positive charge and you have some negative charge. That's why they're sticking together. But the smaller the ions are, the greater the attraction because they can get closer to each other. Remember, by Coulomb's law, the attraction drops off by the inverse of the square of the distance, meaning if they're very big, their centers are much further away, so the attraction is not as great. We want very small ions. Those are going to have a stronger attraction. Then also the magnitude of the charge. So if you have +1, -1, that's not as strong an attraction as +2, -2. That would be stronger. So LiCl and NiCl, we have Li plus and we have Cl minus, and we have Na plus and we have Cl minus. So we have Li plus and Cl minus, and we have Na plus and Cl minus. So because chloride is the same in both cases, but lithium is smaller. Lithium is smaller. They both have a +1 charge, so it's not that. That's the same, but lithium is smaller. So LiCl is going to have a greater lattice enthalpy because the centers of the ions are closer together. So there's a stronger attraction due to the smaller size of the lithium anion, or lithium cation. So speaking of which, this should be very easy. We want to be able to say, if this is lithium chloride, which one of these represents lithium and which one represents chloride? Well, lithium, Li plus, is just has a helium electron configuration. It's only got one shell, right? Whereas chlorine, that's even much bigger than this. That's in N equals 3. So that's way larger. So obviously, this is Li plus and this is Cl minus. We should be able to see just by looking at the periodic table, they're in different periods. Lithium plus is much, much smaller. So very clearly, just based on the size of these circles, that's clearly going to be lithium. Now, the lattice enthalpy of LiCl is positive, indicating that it takes energy to break the ions apart, but the dissolution of LiCl in water is an exothermic process. So what that means is, once again, we were talking earlier about the difference between lattice energy and then the energy of solvation. So always, any ionic solid, it would require energy to pull all the ions apart and away from each other. But then it will always release energy if we put those ions in water so that they can make interactions. Now, which one of those is bigger, that will tell us whether the dissolution of that ionic solid is endothermic or exothermic, right? If the lattice energy is greater than the energy of solvation, then it takes more energy to pull them apart than is released when they get into the water. And we're just dumping the solid in the water, so that makes sense. But in this case, the energy of solvation is greater than the lattice energy for lithium chloride. So more energy is released by solvation than is required to break up the lattice. So it's exothermic. So why is that? What are the particle-particle interactions that contribute significantly to the dissolution process being exothermic? So what are the interactions that the individual ions are making? That's essentially what this question is asking. So if we have Li plus, what is that going to interact with water? Well, that is going to interact with the negative end of water's dipole, right? Because plus interacts with minus, and then the chloride ion is going to instead interact with the positive end of water's dipole. So we need to understand that, and we need to understand that these are ion-dipole interactions, right? An ion interacting with a dipole is an ion-dipole interaction. Makes sense. So this was a pretty good question that was asking about lattice energy and solvation and electron configuration and all kinds of different things here. So this was a lot of concepts in one problem about ionic solids.